I want to talk about my big problem. It's a geometry problem. I've been painting my house the last few months on my days off, as long as I didn't have something else I had to do on my days off, and not with a sprayer or even a roller, but with a brush, with this brush. A little bit of traffic on the busy streets here. But more than just slapping on some color, I've been caulking every crack, patching any hole, repairing anything that needs a repair, replacing any little bit of rotted trim, which there's some. A torn screen is going to be replaced. Any leaking faucet is going to be fixed. One of the pieces of trim that had rotted was a little decorative ring that goes around the attic vent. When I first decided to replace it, knew that it needed to be replaced, my first thought was to make it the seal of Rassilon, because I'm a big Doctor Who fan. But this is Texas. It gets really hot. The attic is 50 degrees hotter than it is outside, and the last thing you want to do is anything that would interfere with airflow out of the attic. So in the end, I didn't do that. I didn't want to cover any of the vents. So I began to work on some ideas that would leave the center open and work out the details that would involve. I settled on a sunburst or starburst sort of pattern, a chain of half circles around a central circle. I thought it would be fun to lay them out using Euclidean tools, just a compass and a straight edge. You have a vent whose center is about 18 inches across. You need a few inches to cover it, to cover the trim. And we need to divide the circle into a number of even divisions. It's easy to divide it in two. Just draw a line through the center. And it's fairly easy to construct a perpendicular to that center point just by working off of increasing the bow of the compass a little bit, and connecting those two lines, and we can divide the circle into fourths. A very similar process can divide these angles, can bisect these angles. It is possible to divide the circle into thirds, and 3 circles are the smallest number of circles you could chain around a circle. You obviously can't chain 1 and you can't chain 2. You could chain 3, although they would be very huge circles. 4 is very easy. Any power of 2, 4, 8, 16, 32, etc., or at least in theory very easy to do. You can do 5. It's a little bit tricky. 6 is dead simple. You cannot, here comes the cat. You cannot trisect an angle with Euclidean tools, except in a few special cases. And one of those special cases happens to be a 90-degree angle. So you could construct an equilateral triangle with a 60-degree angle. The other angle would be a 30-degree angle. And you could bisect the 60-degree angle to get two more 30-degree angles. So you could have 12 circles around the outside. I decided on 16. Here I've done 8 with a little bit of catus interruptus. Yes, kitty. Well, I'm just going to stop at 8 to make it a little bit simpler. So what we want is to find a circle that will fit in this angle and barely touch this circle. That is to say, is tangent to the circle and tangent to these two lines. And I thought to myself, that's obviously doable. There's 3 points, and you can construct a circle through 3 points. Given 3 points, you can construct a circle. However, when I started to try to figure out how do you find the center of the circle, it's out here somewhere, but how do you find that circle? It isn't terrifically obvious how you get there. That's not right. Pull it out some, and now it's getting closer, but that's not right either. Well, maybe you're more clever than I am, but I thought about it for a while and I couldn't see how to find that center. I knew that it would lie on a line that bisected this angle. And it's going to pass through that point. But how do I find the point on this line? How do I find the point on this line that it passes through? Or how do I find the center? And I didn't see how to do it. So I began to think like an engineer instead of a geometer. The saw that I'm going to cut it out with cuts a swath almost 1/8 of an inch wide. So plus or minus 1/8. If it was off by a quarter of an inch, it would be perfectly fine as a layout. And also, if I drew this chain of circles on a given circle, this is still the shape I'm looking for. It's just not the right size. I want this shape where its inner edge roughly is 18 inches across. But what I have is a circle here that's 18 inches across. It's the same shape, it's just not the right size. I want this shape to be out here, going, etc. Except I was going to do 16 instead of 8 circles. So it wasn't too hard to see what to do. If I fire up the mighty computer and lay it out in a CAD program, I could just grab that shape by the corner and drag it up to the size that I wanted, which is not Euclidean methods, but it's going to work. And that's what I did. I laid it out in the computer, plotted it on paper with the plotter, took the paper pattern, transferred it to plywood, cut it out of plywood with a saber saw, had it primed, painted, and installed in a few days. But I could not let go of the geometry problem. It occupied my idle moments at home and at work for longer than I care to admit. I knew that it was solvable, but I couldn't see the solution. Eventually, though, I cracked it, I solved it, and this is how you construct a circle tangent to a given circle and tangent to an angle, a given angle, that forms a slice of the given circle.
First, let's construct our given elements. An angle, the given angle, which forms a slice of the circle, and a circle, the given circle, which is centered on the vertex of the angle. We're going to do the general case, which will work for any angle. I don't know the size of this angle, or whether it would divide the circle into equal slices if you repeated it around the circle's circumference. It probably wouldn't. I just drew it randomly. If you want to construct a chain of circles around the given circle, you would need to divide the circle evenly into equal divisions, as I did on paper earlier, and repeat these following procedures for each division. But if it works for the general case of an arbitrary angle, you can be sure it will also work for those particular angles that do divide the circle evenly. First, we will bisect the given angle. We know already that the circle we are looking for will pass through the point where the angle bisector crosses the given circle. Now we will construct a line perpendicular to the angle bisector, which passes through that point. That is, a line tangent to the circle at that point. We will next mark the points where the line we just constructed intersects the legs of the given angle. From these points, we will pull two small circles that reach the point where the tangent line intersects the angle bisector. Next, on each leg of the given angle, we will construct a perpendicular line that is tangent to the little circle on that leg of the given angle. We will mark the point where these two tangent lines cross each other, and which incidentally lies on the angle bisector. This point is the center of the circle we are looking for. Pull out a circle from this point to the point where the line tangent to the given circle crosses the angle bisector, and we have constructed the circle we are looking for, here shown in red. There's something very intuitive about this construction. You can just feel that it makes sense, and it sure looks like it works. But there are two questions in geometry. One is, how do you construct something? How do you construct a perpendicular line, or an equilateral triangle, a pentagon, etc.? And the other is, how do you prove something? Can you prove that what you have constructed is really what you say it is? Some people think that the construction is the fun part and the proofs are boring. At least a few people see it the other way around. But both are important. If you take a geometry class in school, it will mostly focus on the proofs, and rightly so, because it's generally meant to be your introduction to mathematical proof. It's thought to be a good training for the mind and great practice in logical thinking. We know the red circle passes through the point where the line tangent to the given circle crosses the angle bisector, because that's the way we constructed it. Therefore, it is tangent to the given circle. But does it just kiss the legs of the angle? Is it tangent to the given angle as well? Maybe it comes close but doesn't quite reach, or maybe it overlaps them a little bit. Can we prove that the circle we found, the red circle, is the circle we were looking for, that fulfills the requirements of tangent to the given circle and also tangent to the given angle? How would you prove that? Well, first, let's label some of these points to make reference a little bit easier. If we could show that the length from A to D was the same as the length from point C to point G, and that the length from point A to point B was equal to the length from point C to point B, then the circle that we know passes through D must also pass through G, which for the moment is just a point on the leg of the given angle where a perpendicular line intersects it, not where the red circle touches it. That's what we're trying to prove, because there would be no length missing or left over on the line from C to B to account for any space where the little red circle doesn't reach or overlaps the leg of the given angle at G. can we show these two things? Yes, I think we can, by paying close attention to these triangles. First, look at the pink triangle, from A to B to G. The angle at G is a right angle, because that's how we constructed it, as a perpendicular line. Across the short side of the pink triangle, we have the angle at B. Now, look at the blue triangle, from C to B to D. The angle at D is a right angle, because that's how we constructed it. Across the short side of the blue triangle is the angle at B. The angle at B of the pink triangle is the same as the angle at B of the blue triangle because it's the same freaking angle. Therefore, the remaining angle of each triangle, the angle at A of the pink triangle, and the angle at C of the blue triangle, are also equal. So we've shown that the pink and blue triangles are proportional, that they have the same angles, but not yet that they are the same size, or congruent, as a geometer would say. Next, consider the yellow triangle, from A to D to F, and the green triangle, from C to G to F. The angle at D of the yellow triangle is a right angle, as is the angle at G of the green triangle. We already know that the angles at A and C are the same, therefore the angles of each triangle at F must be the same as well, which we could also show because they are on opposite sides of intersecting lines. But for the yellow and green triangles, we know something else. We also know that the short sides of each triangle are the same length, because the short sides, F to G of the green triangle and F to D of the yellow triangle, are constructed from the radii of the circle whose center is at F. We pulled this circle from F to D to create G as a point on this circle. And knowing that the angles are the same in each, and that one adjacent side is the same in each, we know that the yellow and green triangles are the same size. They are congruent. So we have proved the length from A to D was the same as the length from C to G, the first thing we need to prove. And it follows also that the length A to F is the same as C to F as well. Now return to the pink and the blue triangles. The length A to F is the same as C to F, and F to D is the same as F to G because they are the radii of the circle at F. So the length on the pink triangle from A to G must be the same length as that from C to D on the blue triangle. And since their angles are the same, and corresponding sides have the same length, the two triangles must be the same size. They must be congruent. Therefore, we have also proved the second thing we needed to prove. The length from A to B was equal to the length from C to B. And therefore, the red circle we found, centered at B, that we know passes through D, must also pass through G. You could do the same thing for the other leg of the angle. I hope that's not necessary, but you could if you wanted to. Now, having used those triangles to prove that the circle we found was the circle we were looking for, we can reverse engineer the process and construct those triangles in order to find the circle we are looking for. This alternative construction is a little less intuitive, but it has fewer steps, which makes it a little more mysterious and impressive. We will start in the same way by bisecting the given angle and constructing a line perpendicular to the angle bisector, tangent to the given circle. Next, because we need a point on the tangent line as far from where it intersects the leg of the angle at F as it is from the center of the given circle A, we will pull out a circle from F to A. I want to note this is not the famous Vesica Pisces, beloved of the Pythagoreans. The circle we've just drawn is not the same size as the given circle. It's slightly bigger here. Depending on the sweep of the given angle, it might be considerably bigger. Mark where this circle intersects the tangent line. Now construct a line perpendicular to the leg of the angle from which we drew our big circle, which is centered on F, so that it passes through the point of intersection at C. Where this line crosses the angle bisector, the point B, we have found the center of the circle we are looking for. And this construction yields a fun little bonus freebie, too. If you construct on the same leg of the angle a perpendicular line that passes through the point where our bigger circle crosses the tangent line on the other side of the angle, where this line intersects the angle bisector, we find the inscribed circle that is tangent to the given circle and tangent to the given angle.
So that's my big problem, done and done. I don't have much more to say, but I do have 3 pretty things to show you. First, a completed construction of 16 circles around the given circle using the first method that I showed you. And then a completed construction using the alternative method. And finally, the installed painted trim ring that started the project to begin with.